All right, let's dive into the world of digital electronics. We're going to take a look at this digital counter circuit. Now, I know it might look a little intense at first glance, but we're going to crack this thing together, piece by piece, and figure out exactly what makes it kick. So here it is, the circuit we're going to be digging into. I get it. It looks like a total jumble of lines and symbols, but stick with me, because by the end of this, I promise you'll be able to look at this schematic and not just read it, but you'll even understand how to tweak it. You know, the best way to tackle anything complex, whether it's software or a circuit like this, is to start by identifying the main players. So let's kick things off by finding the most important building blocks here. Okay, right at the heart of this thing, you see these 4 rectangular blocks? These guys are called JK flip-flops. Think of them as tiny 1-bit memory cells. They are the components that are actually storing the ones and zeros that make up our count. They're the brain of the operation. So if the flip-flops are storing the numbers, how do we actually see them? Well, that's where these 4 LEDs come in. Each one is hooked up to a flip-flop, representing a single bit. If a bit is 1, the LED lights up. If it's 0, it stays off. Simple as that. It's our visual readout of what's happening inside. And the last piece of this puzzle, what actually makes the counter, count? That would be this button right here. Every single time you press it, it sends a little electrical pulse, what we call a clock signal, into the circuit. That pulse is the trigger, the thing that tells the flip-flops, hey, time to change to the next number. So let's just quickly recap what this JK flip-flop thing really is. At its core, it's the fundamental memory block. It holds just 1 bit of data, a 0 or a 1. And based on what we tell it, when that clock pulse hits, it can do a few things. It can hold its value, it can flip to the opposite value, that's called toggling, or we can just force it to be a 1 or a 0. It's like the simplest possible computer memory you can imagine. Okay, so we've met the key players. Now let's figure out how they actually work together to get this counting job done. And to do that, we have to answer a really important question. Is this thing a synchronous or an asynchronous counter? Now, what does that even mean? Well, it all comes down to timing. Do all the flip-flops change at the exact same time, like a perfectly synchronized swim team? Or do they trigger each other one by one in a sort of chain reaction? The answer tells us a ton about how this circuit behaves. To figure this out, all we have to do is follow the money, or in this case, follow the clock signal. Look closely. The pulse from our button only goes to the first flip-flop. Then the output of that first flip-flop gets wired into the clock input of the second one, and that pattern just continues right down the line. And that daisy chain connection is the dead giveaway. See, in a synchronous counter, one master clock tells everyone to change at the exact same instant. But here, the first flip-flop has to change before it can tell the second one to change, and so on. It creates this tiny delay that cascades down the line. It's literally called a ripple effect. So, based on that evidence, there's no doubt about it. What we're looking at here is an asynchronous ripple counter. That ripple, that chain reaction, is its defining feature. Awesome. We've identified our counter. Now let's figure out what it can actually do. What's its limit? How high can this thing possibly count before it has to start all over again? 16. This counter has 16 unique states it can be in. It can count from 0 all the way up to 15. But why 16? Where does that number come from? Well, that number has a name. It's called the modulus. And the math is actually super simple. We have 4 flip-flops, right? And each one can be in one of 2 states, on or off, 1 or 0. So the total number of combinations is just 2 to the power of 4. And that gives us 16 possible states, which means our counter can represent every number from 0 to 15. Okay, theory's great, but let's try a practical example. Say the counter is at the number 4. What would you actually see on those LEDs? To figure this out, we just need to translate. The decimal number 4 in 4-bit binary is 0100. So we just match that up with our LEDs. The first LED is off, the second one is on, the third is off, and the fourth is off. Simple as that. Up until now, we've just been letting the counter do its thing, counting up one by one. But what if we want to jump in and take control ourselves? Well, that's where these special inputs come into play. If you look at the flip-flops, you'll see these pins labeled R and S. These are our manual override switches. They're asynchronous, which means they don't care about the clock pulse at all. The R pin stands for reset. Hit that and it forces the output to 0 immediately. S is for set, and it forces the output to 1.
They're our way of telling a flip-flop what to do, right now.
All right, now for the really fun part. We're going to stop just analyzing this circuit and start thinking like engineers. We are going to actually modify this circuit to make it do something new. So here's our mission. We need to take our counter that goes from 0 to 15 and turn it into a decade counter, one that only goes from 0 to 9 and then resets back to 0. How in the world do we do that?
Now here is the clever trick. You don't actually stop at 9. Instead, you let it count to the next number, which is 10, and you use that state as a secret trigger. The binary for 10 is 1, 0, 1, 0. The circuit will hit this state for just a split second, so fast you'd never even see it, because that state will instantly trigger a reset back to 0.
And we can pull this off in 3 simple steps. First, we look at the binary for 10, 1, 0, 1, 0, and see which bits are 1. That's the bits connected to LEDs D4 and D2. Second, we take the wires from those two outputs and connect them to something called a NAND gate. Now, a NAND gate is a cool little logic device that's basically on the lookout for one specific moment, the moment when both of its inputs are 1. Finally, we connect the output of that NAND gate to the reset pins of all our flip-flops. So the instant the count hits 10, the NAND gate sees it, sends out a reset signal, and bam, the whole counter is forced back to 0. So let's just zoom out for a second. We didn't just learn about this one circuit. You've actually just picked up a whole new toolkit for analyzing digital electronics. You now know how to break down a complicated diagram, how to trace a signal to figure out how it works, how to do the math to find its limits, and even how to use logic gates to modify its behavior. We've come a really long way from that scary-looking schematic we started with. You've now got the skills to not only understand what's going on here, but to start imagining what else is possible. So I'll just leave you with this question. Now that you can read this circuit, what could you build with it?